Dr. Mack, hi, welcome to your Speaks to Schools virtual talk. Thank you so much for being with us today.
Hi, it's really great to be here.
Thank you so much. So I think you have a fantastic presentation to get us started, and in the meantime, we'll curate some student questions for you too.
Okay, so I'll just get started then.
Perfect, thank you so much.
Okay, well, hello everyone. I'm excited to talk to you today. What I'll be discussing is how I got interested in physics, how I got into using physics to learn about the universe and what we can see in the cosmos that can tell us about sort of the ultimate nature of reality. And I'll say a little bit also about the book I wrote, which is about the end of the universe and how this big, beautiful cosmos of ours might eventually come to an end. So just by way of introduction, my name is Katie Mack. I'm an assistant professor of physics, and I've always been fascinated by the universe. And a lot of people who study astrophysics get into it because they get, just fascinated by the night sky. You know, they do stargazing and they see this beautiful universe out there, and they want to learn more about that. And that's not how I got started in astrophysics, because where I grew up, you couldn't really see those kinds of stars. I grew up in Los Angeles. The sky was pink. It was not a place where you could do a lot of stargazing and see this, this beautiful night sky. So what really got me interested in science and in astrophysics and in physics in general was just trying to understand how things work. I was always the sort of person who was fiddling with things. This is a picture of me. I'm there in the pink shirt, helping some kid fix his bicycle. I would always take apart the remote control at home. This was the kind of thing, like, I just wanted to know how everything worked. And at some point, I started to read about astronomy and to read about physics and to start thinking about kind of bigger questions. So I wanted to understand how everything worked. I read Discover magazine and learned about mathematics and physics and all these weird sort of brain-bending ideas. And then I started reading A Brief History of Time by Stephen Hawking and learned about black holes and the Big Bang and space-time. And I just got really fascinated by all of those very strange ideas and what we could learn about the cosmos. And so I was in school. I studied hard. There's a picture of me from middle school doing my homework because I was such a cool kid. And eventually I got some opportunities to get involved in research early. And the first place I got to do actual physics research was here. This is the Super-Kamiokande Neutrino Detector in Japan. And what it is it's a giant tank of water. In this picture, you can see some people floating around in a boat inside this tank of water. It's 40 meters tall, and it's filled with this ultra pure, very, very clear water. And the edges of the detector are lined with they're called photomultiplier tubes. They detect tiny, tiny amounts of light. And so what you do is you fill up this tank of water and you use these photomultiplier tubes to detect really tiny flashes of light when a neutrino passes through this detector. This is a picture of me at that time when I was visiting the detector. So the way it works, the way a neutrino detector works is it's underground. So you drive into the side of a mountain and you go through these tunnels. It's in a mine. And you end up in this control room where there's an image of the detector. And what happens is, as the neutrino comes through the detector, what happens is a neutrino is this tiny subatomic particle. It's so small and so weakly interacting. It barely interacts with anything at all. And so when it moves through the universe, it can pass through solid objects without even noticing. There are neutrinos passing through the Earth all the time. A neutrino could pass through a light year of solid lead and have barely any chance of interacting with anything. But every once in a while, a neutrino will run into something. And so that's the idea behind a neutrino detector, is you have this giant tank of water, you put it deep underground so that all of the other particles get stopped by the mountain. And you hope that every once in a while a neutrino will bump into something in your detector. And when it does, it creates a flash of light, and those folded multiplier tubes pick up that light and tell you where the neutrino came from and what it's doing. And so you can use this detector to see these neutrinos. And the neutrinos come from everywhere in the universe. They're sort of passing through the cosmos, but most of the ones we see come from the sun, because neutrinos are produced when the sun does nuclear fusion, when it takes hydrogen atoms and smashes them together to make helium, which is what makes the sun shine. And so you can use neutrino detectors to pick up those neutrinos from the sun, and you can actually use that to take a picture of the sun from deep underneath a mountain using neutrinos. And this is an image of the sun in neutrinos. So this is a picture of the neutrinos coming from the center of the sun, coming from these nuclear reactions. And this picture was taken by this neutrino detector deep underground under this mountain in Japan. So getting involved in that project is one of the things that really got me fascinated by the universe. I was really interested in particle physics. I was really interested in kind of how physics works, and the fact that we could use particle physics, use these experiments, underneath mountains in Japan to learn something about the cosmos, to learn about how stars shine and how the universe works. And by studying neutrinos, you can learn about all sorts of aspects of particle physics and just how everything in the universe fits together. And so as I kept studying, I got more and more interested in astrophysics and in learning about the universe in other ways. And I learned about what you can learn about in cosmology. So cosmology is the study of the universe from beginning to end. It's the study of how the cosmos evolves over time. And I did some work on the very early universe. So what happened at the very, very beginning of the universe? And this is something that you would think would be a hard problem, because, how do you know what happened at the beginning? The universe has been around for something like 13.8 billion years. It seems like it should be difficult to learn about the beginning, but we have a really cool advantage in astrophysics, which is that we can see the past. We can look right into the past. It's like a time machine, but we can just look and directly see the past, because every time we look at something that's far away, we're looking into the past. When we look at distant stars, we're looking at the light that they sent out maybe thousands of years ago. When we look at the sun, we're looking at the light it sent out 8 minutes ago, and so we're seeing an 8 minutes old picture of the sun. But when we look at other stars, we can look at thousands of years ago, and when we look at other galaxies, we can look at billions of years ago. And so every time we look farther and farther away in the universe, we're looking at an earlier time in the universe. We're looking at the universe when it was younger. So an image like this one shows you galaxies far, far away. And so it shows you a universe that's younger than the universe today. And so you can actually sort of map out how far back in time you're looking when you look at different images of distant galaxies. So this is a diagram of the Hubble Space Telescope showing different sort of pictures the Hubble Space Telescope has taken, how far back they're looking. And so we're in the modern universe at 13.8 billion years after the beginning. But the Hubble Space Telescope can see galaxies that were around when the universe was only about 500 million years old. So in the very, early times of the universe. But in principle, you can look back farther than that. You can look so far away that you can look at the time before those galaxies even formed. And what happens then? You see this, you see the gas that the galaxies formed out of, and then you look farther and farther back, and you start to see something really interesting. You start to see the actual Big Bang. So the Big Bang is the idea that in the very early universe, at the very beginning, the universe was hot and dense, and in some sense smaller than it is today. We know that the universe is currently expanding. Galaxies are getting farther apart. Space is getting bigger. And as that expansion happens, the universe cools, which means that if you dial that expansion back, if you go back in time, you find a universe that's hotter and smaller and denser than it is today. And so when you look farther and farther away, you're looking farther and farther back, and you're looking at a time when the universe was hotter and hotter and denser and denser. And everywhere in the universe was hot and dense. So anywhere you look, you'll look at, in one direction, you'll look so far away, you'll see parts of the universe that are so far away, that they're so far back in time, that from your perspective, they're still in the Big Bang. They're still on fire, right? And so you can look every direction in the universe and look far enough away that you can see that primordial fire, you can see that Big Bang light. And that's called the cosmic microwave background. And so when we look out into the cosmos, we see that cosmic microwave background everywhere, because we see parts of the universe that are so far away, that they're so far back in time, that they're still just coming out of the Big Bang. They are still on fire. And we can actually take that light and we can map out that light from the cosmic microwave background. And this is what it looks like if you take that light and you turn it into a kind of light that we can actually see, colors that we can see. And you see this kind of splotchy picture. So this is a projection of the whole sky projected onto a kind of oval shape. And it looks splotchy because there are parts of the universe that were a little bit hotter, and there are parts of the universe that were a little bit cooler. This is during the very, very beginning. This was about 380,000 years after the first moment of time that we can understand. So right when that primordial fire was just starting to cool down. And so we see that that light everywhere, and we see these patterns in that light. And what we can do is we can look very closely at these patterns, these little splotchy patterns in the background light of the universe, and say, okay, this part was a little bit more dense and this part was a little bit less dense. So we can figure that maybe over time, this part that was a little bit more dense will bring together a little bit more matter, and things there will grow, and this part that was a little less dense will have a little bit less matter, and you know, less will happen there. And so we take this this cosmic microwave background light, we take the little fluctuations where things are a little bit denser here, a little bit less dense there, we put it into a computer simulation, okay? So we say, okay, we're going to do a computer simulation. We're going to say that we're going to take the same pattern that we see in the sky from this cosmic microwave background light, and we'll put it in the simulation. We'll say, okay, here, computer, this part has a little bit more density, so you'll let the particles come together over here, and in this part there's less, so the particles won't come together. So you set this up so there's gravity, and you just let the computer simulation run. And so when you do that, what you see is that just as you expected, the parts with a little bit more matter, they have a little bit more density. Gravity pulls matter together there, and the parts that were a little bit less dense get kind of emptied out. And so you end up with this sort of cosmic web, this web-like structure where you have these clusters and these filaments and then these kind of voids. And then you say, okay, based on what we know about how the universe evolved, those places, those little higher density places, that's where the galaxies must grow, right? Because you bring in the gas and then galaxies grow, and then that's where you see stuff in the universe. And so you can take the output of these simulations, and you can say, okay, the more dense parts in the simulation, that's where galaxies should be, less dense parts are where they shouldn't be. And so you can figure out from the simulation what the distribution of galaxies should look like. And when you compare that to what you actually see in the sky, this is a map of actual galaxies in the sky, where in this map, each little dot is a galaxy. You see the very same shape, this very same pattern. You see this cosmic web where there's clusters and filaments. And if you do the statistical analysis on where those things are and how they're distributed, it perfectly fits what you got from the simulation. So there's this fascinating thing where you can look at the background light of the universe, look at little tiny fluctuations in the background light of the universe, give it to a computer, let it run over time, and you get exactly the same pattern of galaxies that we see in the sky. So we have this amazing picture of how the universe formed, how the everything we see in the cosmos formed from the very, very beginning, from those little tiny fluctuations in the afterglow of the Big Bang itself. And one of the things that we discover when we do these kinds of simulations is we discover that that all of that structure is actually not built entirely of the kind of matter that we see today, but out of something we call dark matter. So dark matter is a kind of invisible stuff that kind of envelops galaxies. So when we see a galaxy in the sky, we see these spiral arms of stars, and we see this bright glowing thing with gas and dust and all of that. That's just a little tiny portion of what's actually out there. There's every one of those galaxies is embedded in this clump of dark matter, this invisible stuff. And that invisible stuff is most of the matter in the universe. In fact, when we do those simulations where we let the matter grow, what we're really putting into the simulation is dark matter. Is we're putting in something that is this invisible stuff that acts differently from regular matter. And so we can learn that most of the universe is made of this invisible stuff. And when we look out into the cosmos and we see galaxies out there, we know that those galaxies, all those little points of light, are just a tiny fraction of what's there. And we can actually map out where the dark matter is in the sky. And this is a map of where the dark matter is distributed in clusters of galaxies. And we can do that because we can see how the dark matter is affecting the space that the galaxies are in. And so there's all this invisible matter out there that we're just beginning to be able to study and be able to see where it is in the universe and what it's doing and how it's helping the galaxies and clusters of galaxies grow and how it's building up all this beautiful structure we see in the cosmos today. And so when you see a picture of the sky, you know, one of these gorgeous images from the Hubble Space Telescope where you see lots of galaxies and stars, you have to understand that what you're seeing there is just a tiny fraction of what's really out there. The dark matter is most of the matter in the universe, and for some reason it's totally invisible to us. But as physicists and astronomers, we're able to start figuring out where it is and what it's doing and how it helped build the universe. So I've only got, I think, 2 minutes left, and I just want to say a little bit about the work that I'm doing recently and about what I've been thinking about when I've been writing. And I want to say a little bit about this book I wrote, which is about the end of the universe. So at some point in the last few years, I've gotten really interested in the question, not so much of how the universe began, but of how it will end. So, you know, we've gone from the very beginning, we've built all this beautiful structure in the cosmos. What happens next? How does it end? Like, what's the next step in our cosmic story? And so I wrote a book called The End of Everything, Astrophysically Speaking, and it's about different ways that the universe might end and what those would look like. And I'll say just very, very briefly, I'll give you a lightning overview of the 5 different ways that I talk about in the book. So first one is the heat death. So this is the possibility that the universe as it is right now, it's expanding. And as the universe is expanding, galaxies are getting farther away from each other. And if that continues forever, if the universe just keeps expanding from, you know, started as in the Big Bang as this hot, dense state, it's been expanding and cooling over time. If it keeps going like that, and if it keeps accelerating in its expansion, which it seems to be doing now for reasons that get into dark energy, which is a whole other topic, if it keeps accelerating in its expansion, then eventually galaxies will be so far apart that we won't be able to see other galaxies anymore. We'll be in a universe that's starting to get more and more empty and more cold, and then eventually everything gets so far apart that each galaxy is just completely isolated. And then eventually over time, the stars burn out, everything kind of fades away, and you end up with this sort of cold, dark, empty, lonely universe. Now, the heat death is the one that we think is probably the most likely based on current evidence, but it's also kind of sad. And there are other possibilities. There are things that could happen to the universe that would be significantly more dramatic. One of them is the Big Crunch. So this is an idea that's been around for a while, and it's not the most favored, but it's an interesting possibility where, you know, the universe is currently expanding, but it's still possible that the expansion might stop and that the expansion might turn around. And if that happened, then instead of sort of a slow fade to black, what would happen is that all these galaxies would start moving toward us again. And you would have a situation where everything kind of comes together and you get kind of like another Big Bang, where the universe becomes hot and dense and, you know, smaller again. And that would be exciting and scary because you'd see it coming and everything would kind of catch fire. But we think that's probably less likely to happen, although it would be a very dramatic possibility. There's also the Big Rip, which is an idea where the universe is expanding and it's accelerating in its expansion, and it gets so fast and it expands so much and so quickly that you start to actually pull apart galaxies and pull apart solar systems and then stars and planets and space itself. Then there's another possibility that's called vacuum decay, and that's an exciting one because in that one you have a kind of bubble of a different kind of space that appears at one point in the universe and expands outward and envelops and destroys everything in this very sudden and complete way. And that one's exciting because it's something that it's only recently that we've really started talking about this as a real possibility for the universe. It probably can't happen, and it probably can't happen soon, but if it could, then it could technically happen at any moment. And so we're very excited about that one as physicists, and that's something that I've been working on in my research, trying to understand, is vacuum decay really something that's possible? And if it is, what do we learn about the cosmos? What do we learn about physics by thinking about that? And then the final one I talk about in the book is called the bounce. So this is the possibility that that the universe might go in cycles from Big Bang to Big Crunch and over again. And there's even some possibilities where you have kind of parallel universes that can kind of smash into each other, and every time they collide, they make a new Big Bang. And so we can have kind of collisions between universes, or these cycling universes where the universe goes from bang to crunch, and so on and so forth. And that brings up some really exciting possibilities, and there are interesting reasons to think about that from the perspective of cosmology and also particle physics. So you might be hearing from this presentation that I'm interested in both astronomy, the study of the very large, and particle physics, the study of the very small. And the reason for that is that as we get into these really big questions of how the universe is going to end, where it came from, how it's evolving over time, what it's made of, both of those aspects are really important. We have to understand what's going on with particles to understand what's going on with the universe, and vice versa. And so when we examine these questions, we use tools like the Large Hadron Collider, this giant machine that smashes protons together and looks at the debris that comes out to learn something about how particle physics works. We use instruments like the AMS detector on the International Space Station. This is a particle detector that's looking at cosmic rays coming from space and might be telling us something about dark matter, and just by detecting particles out there in space. And we use telescopes that are examining the cosmos and studying galaxies and their distribution of galaxies, where they are in the cosmos, studying how dark matter bends the space it's in order to, and so we can learn about where dark matter is. We use telescopes to learn about the births and deaths of stars. And we also use just math. So as a theorist myself, I do a lot of thinking that involves equations and thinking through things on paper or on chalkboards. And that's another important part of this whole equation of fitting together how everything works on the smallest scales and the largest scales. And the thing that links all of that is mathematics, is the understanding the structures of mathematics, understanding how everything is part of these big theories and trying to figure out how it all fits together. Now, I don't come up with the theories myself, and I don't do the astronomical observations. The part that I do is kind of the in-between part, looking at the theories, looking at the observations, and trying to figure out how to join those two together, how to find new ways to test the theories with what we learned from the sky and from experiments. And that involves a lot of, thinking really hard about the problems, talking to people who do the theory, talking to people who do the observations, and trying to find new creative ways to bring it all together. So that's the end of my presentation. I think there will be questions. So thank you for your attention.
Absolutely. We have a lot of questions submitted, Dr. Mack. Thank you so much for that. They've tended to fall into three categories. One group of questions are focused on your career and your inspirations. Then a lot of questions about your work. And then also questions around young people who might have an interest in your sector and any advice for them pursuing that as well. So if it's okay with you, we will start with a few questions about your own career and inspiration. And one of our students here, Tallulah, has asked, when you heard of astrophysics, did you know straight away that's what you wanted to study?
It was pretty quick. So I think I was about 10 years old when I first started to learn. What happened was I was reading A Brief History of Time, and I was learning about black holes and the Big Bang and stuff like that. And you read A Brief History of Time, you learn about Stephen Hawking, and I learned that Stephen Hawking, his job title was cosmologist, and I was like, okay. Clearly, I want to be a cosmologist. At that time, I didn't really know what that was, but I knew that's what I wanted to do because I wanted to learn about the universe. And I think I was probably about 10 years old when I figured that out. So for a long time, it's definitely been something that I've been working toward.
That's fantastic. And I know you mentioned you're even reading Stephen Hawking's work. Would you say that he was an inspiration for you to follow a career in astrophysics? And are there any other, I guess, inspirational people that have helped you along in your career?
Oh, yeah. I mean, there have been so many people. He was definitely an inspiration to me, and I was fortunate enough to meet him a few times. I worked for a while at Cambridge University, and I got to interact with him there. He came to a talk of mine once, which was very exciting. So he was a big inspiration. I had other, I had teachers and people I worked with in research. When I worked at the Neutrino Detector in Japan, I worked with a professor called Professor Kenneth Gneuser, and he really sort of took me under his wing and taught me a little bit about physics, and that was great. And then I had other kind of role models and people who I learned a lot from. So, too many people to name, but there were definitely a lot of people I looked up to and who I learned a lot from.
Fantastic. One of our students also asked, how long did it take you to write your book?
I think it was probably about 18 months total, but it's a fuzzy thing because there are revisions and there are edits, and but the actual writing maybe about 18 months, something like that.
Fantastic. And just one very quick question before we move on to some very interesting questions about your work. One of our students here has asked, do you have a favorite planet and why?
Okay, so I have to show you something. This is my phone background. That's Mars. I think that I mean, I love the Earth. I live here. It's beautiful. But I'm really fascinated by Mars because it's so close to being Earth-like. You look at these pictures and it's like you could walk around. You can imagine hiking up these hills and dunes. There's riverbeds on Mars. They have like these dust devils that roam around the surface. There's so many fascinating things that happen on Mars that I would really love to go there. So I think that I've been seduced by the idea of wandering around on Mars, and I think that's why I am so obsessed with it.
I think that's a great reason as any other. One of our students here, Annabelle, has asked, do you believe in the multiverse theory?
Ooh. I have such a long answer to this. There are lots of different kinds of multiverse. So it really depends on what you mean by multiverse. There's the idea that there are parallel universes, that every time you flip a coin, it lands heads in this universe and tails in another universe, and then it sort of branches off. That's called the many worlds idea, the many worlds interpretation of quantum mechanics. It's not really coin flips, but quantum events that sort of branch off new universes. And that's something that I've read a lot about. I don't really have an opinion either way on whether or not we have that really happens with quantum mechanics, but it's an interesting idea that there are different universes that are just very slightly different and branching off all the time. But there's also multiverse ideas in physics, in astrophysics, in cosmology, where you can have our universe sort of might have formed, and then another universe might have formed sort of nearby, and they could have all these little universes kind of popping out of whatever process formed our universe. And so there could be other universes out there that are far enough away from us that we'll never be able to interact with them unless one sort of smacks into us, like I talked about a minute ago, and that's a whole other story. So there could be just regions of space that are so far away from us that they're effectively separate universes, and that's something that I think that is actually fairly mainstream, that in cosmology, that there are parts of the universe that are so far away that they're basically separate. So I think that's probably true. And then there are a couple other possibilities for multiverses that I won't get into because I don't have time. But I think the cosmology one I definitely think is very likely. The quantum mechanics, I'm not sure. I haven't decided yet.
One of our students here has asked a very interesting question. If you travel anywhere in the universe, where would you go?
Okay, so I think we've already established Mars is one place.
Absolutely.
I'm not sure. I mean, I would love to travel to like a planet orbiting a star inside a nebula to see like what that would look like with your eyes. You know, like would you really see those amazing colors, or you know, a star on the outskirts of our galaxy, so you could see our galaxy in the sky, like the whole thing. That would be pretty cool. Or maybe in the center of the galaxy. Like there are just a lot of places that would be really neat. Or a planet with rings. I would love to be, like, if there's a terrestrial planet with rings out there in an atmosphere, that would be so cool. I don't know. I would love to see everything. If I had a faster than light spaceship, I would go wild.
Fantastic. One of our students here has asked, is it possible that maybe the universe isn't expanding, but instead is being pulled or rushed towards a gigantic black hole somewhere out there?
So people have looked at this. So the problem is, if you the way it looks from here is, what you actually see is you see every distant galaxy moving away from you. Okay, so when we look at distant galaxies, it looks like every distant galaxy is moving away from us, and the more distant ones are moving away more quickly. So it wouldn't work for everything to be moving toward one thing, because then they would, you know, the ones over there would be moving toward us, right? Because we'd all be moving in the same direction. So the only way that everything can be moving away from us is either we're just really repulsive, or the whole universe is expanding. And I think the more likely one is that the whole universe is expanding, and if it's expanding in the same way in every direction, so just space is getting bigger everywhere, then it makes sense that the more distant things are moving away faster, because, you know, as space expands the same everywhere, two things that are close together will get a little bit farther apart, but two things that are already far apart, there's more space in between them to expand, and so they get farther apart much faster. And so you end up with distant things are moving away much more quickly. And that idea of uniform expansion fits the data better than anything else. And people have looked at all kinds of other possibilities, but it really seems like it's just totally uniform expansion.
Excellent. Dan has asked, do you think dark matter is made from, I don't know if this is WIMPs or WIMPs?
Yeah. So WIMPs, that stands for weakly interacting massive particles. And that weakly there means both not interacting very much with regular matter, but also it's usually used to mean interacting with the weak nuclear force. We know that neutrinos, for example, are particles that interact via the weak nuclear force. They are weakly interacting massive particles, so in the sense that they're also a kind of dark matter, because they have a little bit of mass and they interact weakly. But we know that neutrinos can't make up, or at least the neutrinos that we know about, can't make up the dark matter, you know, the stuff that's most of the matter in the universe, because there's just not enough mass, and also they move too quickly. They don't fit the data very well. But the idea that the dark matter that we know is out there, that's most of the matter in the universe, the idea that that's some other kind of weakly interacting massive particle is it's an idea that's been around for a long time, and we think it might be true, but there are other possibilities as well. So there are also possibilities that it could be a totally different kind of particle, like an axion, which is a sort of exotic hypothetical particle that is associated with the strong nuclear force, or sort of it's associated with problems in the strong nuclear force. That's a long story, but that's a possibility. And then there are other possibilities, like it could be tiny black holes. That idea has been around for a long time as well. So I think that weakly interacting massive particles are kind of the most likely scenario, but also we haven't detected them yet, and we've been trying for a long time. And so that's at least in terms of the interacting with the weak force part of the question, people are starting to really doubt that that is the correct explanation. So there are a lot of ideas about dark matter out there right now. There's which is really fun because there are all these different possibilities that are fun to think about. And I try to stay kind of agnostic on it because I don't want to get too biased because I'm working on it myself, you know. So I don't want to get too invested in an idea. But in the research I do, we usually assume it's weakly interacting massive particles, and then kind of say what would the consequences of that be, and then we can maybe rule them out or hopefully someday find them.
Thank you so much. One of our students here has asked, is it possible for the light of a star to be refracted around a dark matter, causing an optical illusion to be created so that a star appears closer to Earth than it actually is?
Oh, okay. So I think that this is referring to the phenomenon of gravitational lensing, which is something that does happen. So with gravitational lensing, what happens is when you have something massive in the universe, that could be a star or a black hole or a planet or a clump of dark matter, it actually bends the space that it's in. So you create these kind of dents in space-time, right? So when something massive bends the space around it, it kind of pulls the space in, and that means that if there's a light beam traveling past, that light beam is kind of pulled in toward the object or the clump of dark matter or whatever, and so that light gets bent around and kind of focused. So if you're looking out into the sky and there's a clump of dark matter in between you and whatever you're trying to look at, it will kind of pull the light around and kind of magnify things in the background, stretch out the images, make things look like they're in more than one place. So we definitely see magnification of images from gravitational lensing. We see distortion of images from gravitational lensing, and that's how we know where dark matter is. That's how we map out dark matter. So in that presentation, I showed an image of a sort of map of where dark matter was in this picture of galaxies, and the way we know that is by looking at this distortion of background light from the dark matter in between.
Wonderful, thank you. We have a question here from Varun relating to the heat death theory. And Ron asks, does the heat death theory relate to the laws of thermodynamics?
Yes, yeah, so the word heat in heat death doesn't actually refer to like hotness, like fire or anything like that. It refers to the thermodynamic kind of definition of heat. So heat in physics is a word for sort of disordered energy, and the heat death is when you have the universe evolves toward a state of more and more disorder, because the second law of thermodynamics says that over time entropy increases. Entropy is just disorder. So the second law of thermodynamics means that that over time things can only get more and more disordered, and you know, it's the same reason why you can't have a perfectly efficient machine. You'll always lose a little bit of energy to heat as you're running the machine, you know, friction and stuff like that. And so that kind of happens with the universe. The universe loses a little bit of energy to heat all the time. And so when you get to the final stages of the universe and the heat death, what's happening is that everything's decaying and everything is kind of burning out, and all the energy is turning into this totally disordered energy, this heat. And so so in the end, the universe is empty of everything except just like the waste heat of reality, and the waste heat of the cosmos. And so the heat death is the death of the universe by turning into waste heat. And so then we get to that stage where it's just waste heat. There's no order, there's no structure left in the cosmos, and at that point, basically nothing happens anymore. And that's a kind of final stage of the universe.
Thank you so much, Dr. Mack. We've also had a lot of questions here from our students who might now be thinking of a career in physics or astrophysics, which is very exciting. And Matthew's asked, what advice would you have for someone who is going to study physics at university?
So, I mean, I don't know. I think, have fun with it, right? I think it's such a fascinating subject. I mean, my advice, one piece of advice would be to really, try and get a really good, solid basis in mathematics. So, and I don't mean be a math genius from the get-go. I was never a math genius. I've always enjoyed mathematics, but it's the sort of thing where even if you don't feel like you're good at it, you practice, you learn more, you get better at it. It's like learning a language. Sometimes for some people it'll take more practice, it'll take more hard work, but you can get there and you can become really good with mathematics, and that's an important thing to do as a kind of investment in doing physics. So I would definitely say, try and spend some time building up that basis in mathematics, and also try and find ways to connect what you're learning with real science that's happening out there. So it's helpful to keep the big picture in mind, and to stay to sort of stay connected to actual research and discoveries and stuff like that. So that would be part of it. Yeah, and don't be afraid to work hard. Having to work hard doesn't mean you're not good at it. It doesn't mean you're not supposed to be doing it. So that's something that's been important to me. I've always had to work hard. It's never come easy to me, but I've enjoyed it anyway. So don't get discouraged if it is difficult. But I think it's it's such a fun topic. There are so many amazing things you can learn, and I really enjoy it.
That's fantastic. And I think that also answers a question from another one of our students who asked, how much do you rely on mathematics, and is it possible to be a physicist without much math skill?
Well, I mean, I don't think you have to be like a math genius, and I certainly am not. And the kind of work I do, even though it is theoretical, it's not the kind of super heavy mathematics that I think people might imagine when they think about theoretical physics. So the work I do is very creative. I'm very conceptual, and I use a lot of programming, but I don't do a lot of super intense mathematics all the time. I do that once in a while, but it's not sort of my main job. So, but don't be intimidated by math. I think it can be something that is really, it can be really fun, and it can be a very useful tool, and you don't have to start out being good at it. So.
Fantastic, thank you. We have time for two last questions, if that's okay. So one of our students, Mansour, has asked, was it difficult finding a research position after you completed your PhD, and is that something people might struggle with?
So for me, it was, it depends. It depends on the year. It depends on what kind of things you're interested in studying, where you're at, how things have gone for you with your PhD, how many connections you've made. So there are a lot of things that come into how difficult it is to find a position. So it wasn't too hard for me the first time I applied. So I've done 2 postdoctoral fellowships. The first one, it was, I had several offers. The second one, it was a little bit harder to find a place, but both times I did find a place to work. But I think that the thing is, if you're looking into studying physics and you want to go into research, when you do your PhD, you're already doing research. Your PhD is 5 years or so, depending on, or 3 years, 5 years, somewhere in there, depending on where you're at, how quickly it goes. You're doing actual research, you're writing papers, you're doing actual discovery. So it's not that you have to wait till you get a research position to do that. And then as you do your PhD, a lot of people find that they don't want to continue in research, and then they find amazing work outside of research physics. And some people do continue in research, and then they go on to the research phase. So you don't have to know right now if that's what you want to do, if that's what you can do. If you want to get into physics, studying physics is an amazing jumping point for a lot of different careers. So as long as it's something that's fascinating to you, as long as you're excited about it, don't be too worried at the opening stages about job prospects, because getting an undergraduate degree in physics and getting a PhD in physics, both of those give you amazing options. So, you know, I would focus first on doing what's fascinating to you. And also, while you're at it, you know, look around at what kinds of jobs physicists go into, because it's not all academic research.
That's wonderful advice. Thank you so much. And finally, quite a few of our students have asked, could you tell us a little bit about what's on the chalkboard behind you?
Sure. Yeah. So this was a sort of a prop for another public talk I did, and I've just been kind of leaving it here. This is a diagram of a reaction, an interaction between dark matter and regular matter, where dark matter particles can come together and annihilate with each other and then create regular matter. So DM stands for dark matter, SM stands for standard model, which is the theory of particle physics of regular matter. And so this is dark matter annihilating and then producing regular matter. That's what that part is.
That's fantastic. I think it definitely intrigued quite a few of our students during the session, which is brilliant. But Dr. Mack, thank you so much. Unfortunately, that is all we have time for today, but a huge thank you for joining us. I think we had a lot of excellent questions submitted from our students, so sincere apologies we couldn't get to them all, but we will share them with you so you can have a kind of a look at some of the questions our students were coming up with and were asking, if that's okay. Yeah, but thank you so much for making the time to engage with us and our schools and students across the whole of the UK. It really is appreciated.
Thank you. It was a lot of fun.